Okay, so this first series is going to be on the book Hands-on Machine Learning with Scikit-Learn and Tensorflow. It's a great book, incredible book, and each video is going to be kind of like one chapter and just going over the chapter, everything that I talked about, and trying to explain those things. Um, the first chapter is very basic, sort of what is machine learning. So these are the topics that are going to be discussed today. I hope there's some editing going on. And the first topic is what is machine learning? So basically, um, machine learning can be defined as the science or art of programming a computer so that it can learn from data. The idea is that it is able to learn without being explicitly programmed. Um, from that, we usually have a training set, which has all the data that is going to be trained and learned from. And every single training example inside of this training set is called a training instance. And to get to the training sets to the actual predictions, the actual thing that is going to learn and make the predictions and sort of be adjusted to do so is the model, which hopefully everything is in place in the video. And so, why would you really use machine learning? I think there are a lot of sort of obvious answers to this, but just to give a quick example, if you think about spam, right, detecting spam in your email, let's say you were to do that manually. So you try to create a program, you try to sort of, what would you do? You would look at a bunch of spam emails and try to see which words they usually use and try to maybe make a program to detect, okay, if they say, give me your credit card or send me all your money, that is a scam. You could do that and sort of program that manually, but the problem here is that, well, first of all, you would have to look at a bunch of emails and you would have to manually sort of put a huge rule sort of program to look at all these different rules and all these different words yourself. So that's the first problem. The second problem is, let's say your program works, and let's say that after 1 week, the spammers catch on to this and see that it's not working anymore, so they change up the wording. Then your program is basically done. It has nothing that it can do. It's defenseless against this. Whereas a machine learning model, it would immediately sort of just, if you fed it all this data of spam, it would look at all that and it will sort of be able to find the exact patterns and the little things and changes that make up a spam. And not only that, but if you also show, okay, this is spam, this is not spam, and it learns this, and then a week later they change the spam to something else, the computer will see this anomaly. The machine learning model will notice that there's a change here, and will also maybe find a pattern that is not exactly words, but a sort of pattern or a way of wording that can be attributed to the new kind of spam as well. So it's a great way to sort of learn a lot really quickly and find these patterns even when it's new, and also learn more about the problem by the computer telling you the specific patterns that are in the problem. You understand what is a spam better than you would if you kind of just looked at a bunch of spam and tried to sort of gauge it out yourself. So that's kind of one a good way of sort of explaining why we use it. Hopefully I'm giving enough space here to show some pictures here, or just to help with the visualization. But next thing we're going to be talking about are types of machine learning. And we're going to start off with the most basic one there is, which is supervised learning. And there are two main supervised tasks that machine learning models usually do, and that's classification and regression. So classification would be, for example, you giving it a bunch of photos of cats and labeling them as cats, and giving it a bunch of photos of dogs, labeling it as dogs, giving it a bunch of photos of turtles and labeling it as turtles. And then you essentially give this to machine to allow it to connect the photo to the label that you gave it. And so it learns that turtle is this type of animal. And so when you give it a photo of a dog later, it's going to read back and see the predictions that they did and kind of what it learned, and give you an output, yeah, this is a dog. In terms of regressions are more like numerical, and they have target values. So for instance, if you're trying to predict the value of a house, you could give it a bunch of data from all over the United States of houses and their bedroom sizes, and then the neighborhood they're in and how close they are to the ocean and all these different features, and give the price of those houses. And so when you want to look at a new house, or maybe you have a house and you want to sell it and you want to know what price would be fair for it, you can give to the model the features for your house, and it will kind of predict to you what the value of that house should be based on what it learned before. So it's more like a regression task. So the next one, which is again a very, very common one, is unsupervised learning, which the whole idea behind it is that you don't really have the labels. Like we gave the example of dogs having labels of dogs and turtles having labels of turtles. In this case, you don't have the labels. You kind of want the machine learning algorithm to find the things for you that you can't really see. And one potentially really good use of that and one good example is, let's say you have this entire clientele database of all your clients for your product, and you want to learn more about your clients. So you could use a clustering algorithm and a super unsupervised learning algorithm and tell it, okay, try to separate my clients into three close groups, right? So it would do that, and maybe you could uncover things that you didn't really know. So maybe you could see that one third of your clients are all pregnant mothers by the age of 30 to 40, and another group of clients are, I don't know, teenage girls between the age of 14 and 18. And so maybe by doing this, you get a bigger insight and a bigger understanding of really what your clientele is, and you can maybe do better ads because of this. You could do an ad that targets especially pregnant women between these ages, and you can do an ad that says, oh, are you pregnant and are you between this age? Well, maybe my product is good for you, right? So who knows? So that's kind of one application. Of course, there are millions of others, but these are just sort of quick examples to them. So three more kind of really good examples of unsupervised learning are dimensionality reduction, anomaly detection, and association rule learning. So dimensionality reduction is something that you can actually use to pick out the best features for your model, right? Because sometimes, let's say you're trying to predict the weather. And well, I guess suppose a better example would be, let's say you're trying to predict housing prices, right? And you have all these different features like amount of bedrooms, amount of bathrooms, amount how close it is to the ocean, all these things. And let's say you also have you have two features that are amount of pillows in each bed and amount of bedrooms, right? And so generally speaking, with machine learning and with these models, one of the things you kind of want to try to do is have mainly useful features, right? So sometimes you need more features, sometimes you need less, but generally speaking, you want to try to slim it down to the most useful features for your model to predict, to make prediction a little easier. Like this is an extreme example, but if you're trying to predict weather and you're using temperature and humidity and air and how many dogs are in the park, like that's not really a good thing to help with the prediction, right? So generally speaking, you want to slim it down to the most useful things, and dimensionality reduction helps with that, because if you gave an unsupervised learning algorithm access to these features, it would tell you that, for instance, number of pillows and amount of beds are really correlated and they're basically in the same group. So you can just turn those two into one feature of amount of beds, and therefore making your model more efficient. The second thing, which was anomaly detection, is one thing that can be used, for instance, for credit card fraud detection. So the idea here is you feed the model a bunch of good credit card transactions, and it's just like reading all the new credit card transactions, and whenever it sees one that seems very different from the group that you gave it, it detects it as an anomaly, and it says, okay, this is weird, this is probably fraud, and so it detects it, and you can use it as such. And the last one, which is association rule learning, the whole idea there is that, and this is really cool, which is, let's say you're a supermarket, right? You're a supermarket and you kind of want to decide how to put things in each aisle and organize things. One thing that you could do is you could use unsupervised learning to use association rule learning, which is you could see which products usually are bought together. So you can see that people who buy barbecue usually also buy ribs, which also usually buy steaks and charcoal. So you could see these groups forming by using unsupervised learning, and you could just put your aisles that way, and that way you could help the user experience and help the business grow and all that. So that's another great application. I'm going to try and change the background here just to make it a little more dynamic, so I'm sorry about the lights. But yeah, just some final three types of learning that can be used in machine learning are self-supervised learning, semi-supervised learning, and reinforcement learning. So try to give it some space here to maybe have something going on here. So with semi-supervised learning, the whole idea is that you essentially, let's say you have a group photo, or you have your Google Photos, right? And you have all these pictures with all these different family members. It could be a two-step process of first being unsupervised learning, in the sense that it first identifies that, okay, this person is in all these photos, this person A, I'm not really sure what it is, but I can tell that there is this person who keeps showing up in these photos, so I'm going to classify this as person A. That's what the unsupervised learning algorithm is going to do. And then it becomes semi-supervised learning when it asks you, do you know who this person is, this person A? And when you look at one photo of person A, you say, oh yeah, that's my brother Samuel. And so what it's going to do now is it's going to automatically label all the other person A tagged photos that the program thought it was similar to this as Samuel. So in a way, yes, it has a labeling, but the labeling comes after being unsupervised. So that's why it's kind of semi-supervised learning. In terms of self-supervised learning, the whole idea there is that it's essentially like you give it less features, and you want it to fill in the remaining features. So for instance, let's say you fed it a bunch. Let's say you have a bunch of photos of cats, and the label are the photos of cats, and the training sets and the inputs are the photos of cats but without their face. You just black out their face, and essentially you want to train it to get to the edited photo with the black face to the normal photo to the normal face, right? So the idea there is that it kind of, although it has a label, you're trying to fill in the missing features, right, from the inputs to the original. And this can be used for a wide range of things. For instance, when you see all those Google ads of, oh, now you can take out people from background photos just to show the background. That's kind of what it does, right? So you can take a picture of your park, and there's a bunch of people in the park, but you only want the picture of the park and not the people in the park. So you can just blur them out by using self-supervised learning. So the machine is going to try to fill in the image to what it thinks should be filled in there, which usually isn't the people, right? It's just the park. So yeah, that's an application. And finally, maybe move around here a little bit. Yeah, the camera's little. Okay. So finally, for reinforcement learning, the whole idea behind it is it's actually very, very cool, and it's used a lot in games for games to be automated and win against humans, right? So the whole idea behind it is that you have an agent. Let's say it's like a little robot, and it's in an environment. Let's say this agent is a chess player, right? Chess player A. The environment is the board. It has the observations of the board, and it has the state, which is where the agent currently is. So if you move a piece on the chessboard, your state is that current piece and all the other pieces and all the other pieces from the opponents as well. And so the agent does actions based on the reward and punishment of each action. So if he moves a piece in a way that makes the rest of the game worse for him, he gets punished. If he moves a piece in a way that makes the game better for him, it gets rewarded. And this way it kind of learns to find the best, most rewarding move at each point in the game, in a chess match, for instance. So that's kind of a little bit of what reinforcement learning is. And finally, just to finish off this section, the difference between batch learning and online learning. So batch learning is when you learn all the data all at once, right? So this usually, it has a lot of data. It is really sort of computer heavy and computer resource heavy, right? It just takes a long time to just go through all the data and you learn all that. And the main problems with that is that, well, first and foremost, it takes a long time. And secondly, there is this thing called model rot or data decay, which is this whole principle that your model is not going to work as well as it did now in the future. And that is because usually things tend to evolve, right? So if you consider, for instance, fashion, right? Let's say you analyze all the available fashion data right now. Your model may be really good today. It may be really good next month, maybe by the end of the year, but give a couple more months or a couple more years and fashion is going to completely change. Like the things people like, the things that are the trends, that might completely change and your model won't be able to predict those things anymore. So you kind of have to update it every now and again. And of course you can use batch learning and sort of try and do that maybe every other week. But again, like this is just a lot of data, right? So it's going to take a lot of time. And so one thing that you can do is use online learning. And the whole idea with online learning is that you get to feed it little bits of data and it learns a little more each time. And this is usually good if you need it to learn a lot, like new data constantly, such as like predicting the stock market and things kind of like that. And so you can use mini batches, which are essentially just smaller bits of the whole data to learn on that as an addition to what it already learned before. So that is usually a really good thing
to do. And one way that you can sort of tune how much it learns new data is by setting the hyperparameter of the learning rate. If you set it to too high, it's going to be very sensitive to the new data and it might react a lot to the noise. But if you set it too low, it won't react to the noise as much, but it might not learn as much as you'd like. So it's kind of depends on you, what your objective is there and what you're trying to do.
So on to the main problems that occur when working with machine learning. And I'm going to try to have them over here, hopefully. I think maybe, yeah, they should be there. So the first one is insufficient amounts of data. So usually with machine learning models, you gotta have tons of data. And this usually means close to the thousands and tens of thousands and sometimes even the millions sort of training samples for the training data to actually learn effectively and be able to generalize pretty well. So you need a lot of data. And the second problem is the sort of type of data and how much it represents the actual data. So let's say, for instance, your goal is to find to what extent do people in the UK like dogs, right? And you find there are 10 million dog owners in the UK. So let's say you survey all those 10 million dog owners. That's a lot of data. That's 10 million. So you definitely hit that mark, but you've only surveyed dog owners. So most likely they're all gonna like dogs. So that's not really representative of do UK people like dogs. You're trying to find out if dog people like dogs, which is kind of a dumb question, right? So that's another one. And then there's poor quality data, which kind of leans a little bit into that, but not too much, which is the whole idea that in your data you might have some outliers, you might have some missing data. Maybe you have this survey and a lot of people didn't answer some of the questions. So you have to kind of figure out how do you fill those holes? What is the most ethical and most sort of technical way of filling those holes in a way that doesn't really mess with the whole findings too much, right? So that's another big one. So the next thing is irrelevant features. And we kind of touched on this a little bit in the beginning, which is the whole idea that I give the example of weather, right? So let's say you're trying to predict weather and you're trying to predict it based on temperature, humidity, air, and number of dogs in the park. You really don't want to have a number of dogs in the park because your model, although it's a very, especially deep learning, is very effective in sort of putting less importance on the things that are less important, like dogs in the park, it still can have an impact on the sort of decision making, the sort of predictions, because you're throwing all these irrelevant numbers in it, and it is trying to think of how am I supposed to use these irrelevant numbers to predict this important thing. So, and as we said, one way of sort of fixing that is using some unsupervised learning techniques. But yeah, that's something we always want to try to have the most useful features available. And then the next two things, they are very, very common within machine learning, are overfitting and underfitting. So the whole idea with overfitting is that your model is too complex or learned too much about the training data and it's not able to generalize well to new data. And usually how this happens is, well, there are some ways to solve this. One way is to getting more training data. Another way is to setting some constraints on your parameters or maybe decreasing the number of features that you give it. And the whole idea here is that the more parameters it has, the more degrees of freedom it has to sort of try to mold itself to the training data, right? And you don't want it to mold it too much, because if it molds too much to the training data, then when you give it new data that it hasn't seen before, it's not going to be, of course, not going to be exactly like the training data. So it's not going to be able to guess well or predict well based on new data. So generally speaking, you want to give it some constraints. And one way of doing that is using regularization, which is the whole idea of sort of being able to decrease some features or some sort of parameters to the point where it makes the model less complex. It makes it a little more simple so that it can generalize more to new data. And finally, underfitting is the exact opposite. So the model is too simple. It didn't learn really enough from the training data, and it doesn't really work well elsewhere, right? It's not as complex as it should be. And kind of the solutions to that is just kind of doing the opposite of what the solutions of overfitting were. And finally, the last section is testing and validating. So the whole idea here is that the way that you kind of see how your model works is by separating, on a very basic form, is separating into the training set where you actually use it to learn and sort of try to figure out how the data actually works. And then you test it on the test set to see how well it works on new data that it hasn't seen before. However, and this is kind of known as the generalization error, is how badly it is able to predict new data that it hasn't seen before. However, one problem that can happen with this is that sometimes you see the generalization error and you see how wrong it is in the test set. So you try to tune it and you try to change some parameters, and then after 100 tries, it's finally better in the test set. But sometimes the problem with that is that you're actually manually sort of making it better so that it works on the test set. And so you're not actually using new data, you're now just sort of trying to fix it to the test set. So one way to solve this is using holdout validation. And this is a very like important technique, which is splitting the data you have available into the training set, the validation set, and the test set. So the whole idea here is that the validation set is going to be the one that you're going to use to see sort of tune, right? To sort of tune your hyperparameters so that they work better to new data. So you train it on the training data, you see how well it performs on the validation data, and based on that, if it goes really badly or it's overfitting or underfitting, you try to change the training data, and you do that until they seem okay. And so by the end of that, you can then finally test it on the test set and see how well it does there to completely new data. And that way you kind of tend to check all the marks. Of course, it is still possible to do the same thing to the validation set that you did to the test set, which is sort of manually change it so that it only works to that one. But it is one really big step forward, I would think. So yeah, that's pretty much it. I hope this video hasn't been too long. I didn't really check how long the total thing was so far, but I hope it wasn't, tedious or anything. But yeah, that's just a really quick introduction. I'm going to try to do one of these maybe once every 3 days or so. I hope the editing wasn't completely disgusting. Maybe it was fine. I hope. Let's see how that goes. And yeah, that's pretty much it. I hope you have a great day. See you. Oh, also bonus content. I completely forgot about this bit. One issue with using validation sets is that sometimes you don't want it to be too small because then it's not really going to represent the data too well for you to learn from it. But you don't want it to be too big because then it takes up too much data and you don't have enough data to train and actually learn. So one solution to this is using cross validation, which the whole idea is that you many times take a piece for validation, you train it on the training data, you evaluate it on the validation data, and then you tune it, and then you redo that again. So you take another piece for validation, and then you use the rest for data, and you do that over and over and over again. And that way you kind of can use small bits of validation, but in total, you're going to get an average that has a lot of total sort of evaluation and looking into the data. The problem with this is that it would take the amount of time it would take to train would be the time it would take to train times the number of validations, right? So could take a big while. So yeah, that's just some bonus content in the end there. And that's it.